before we start our joint class, let's pray together. Bismillahirrahmanirrahim. Allahumma sholli ala Sayyidina Muhammad wa ala ali Sayyidina Muhammad. Allahumma firli dunubi wali walidayya warhamhuma kama rabbayani shaghira. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Rabbi zidni ilma warzuqni fahma. Amin ya rabbal alamin. Can you hear my voice clearly, Rizka? Yes.
Yes, we can hear.
Okay, so we will taking picture before we start our class. So please display your name correctly. So there is a student ID and then the nickname. And then please open your camera. Nabila, can you help us to taking a picture?
Yes, I can, Dr. Vera.
Thank you.
Wait seconds. Okay. Okay, please turn on your camera. I'm going to take picture. There are 2 slides right now. And please change your display name according to the format that I've sent and Dr. Vera sent to the room chat. Are we ready? I'm going to take the picture now. Please turn on the camera and change your format name. For the first slide, 1, 2, 3. Wait. One more for the first slide. 1, 2, 3.
Okay, finish?
Not yet. For the second slide, not yet, Dr. Fer. Okay, now the second slide. 1, 2, 3. Okay. Let me check it. One more for the second slide. 1, 2, 3. It's done, Doc. Thank you.
Okay, thank you, Nabila. So today, Dr. Lucia will deliver the course. So today she will explain about the module A2. So please pay attention because the module A2 will do to this Saturday, right? So Dr. Lucia, time is yours. Are you ready, Dr. Lucia?
Thank you, Dr. Vera. Can you hear my voice?
Yes, clearly.
Okay. Can you see my screen, Dr. Vera?
Yes, Dr. Lucia.
Okay, all right, guys. So today we are going to make a quick review what we do in Module A2. As Dr. Vera has said, Module A2 is due this Saturday. You have collected Module A1 yesterday. So now we are going into Module A2. The title of Module A2 is about hydrogen atomic orbitals. Okay, so we will start with the objective of Module A2. The same as Module A1, Module A2 also has two objectives, and it's not so much difference from the objectives of Module A1. The two objectives for Module A2 are, first, we should distinguish the physical and computational problems. So as you can see, about these physical and computational problems, Dr. Febrian and also us keep repeating about these problems. So hopefully after learning Module A1 and also continuing with Module A2, we all will be able to understand which are the physical problems and which are the computational problems. Our second objective is to check the validity of the FT calculations with hydrogen atomic orbitals. In the previous module, we checked the validity of our calculations using Hans rules. But this time, we are going to use hydrogen atomic orbitals. And the additional, we will develop a good practice to organize massive numeric data. Yeah. We will have a lot of data in this calculation. The same for module A1. Now, before we go into the module, oh, I will give a little bit introduction. Can we predict all the properties of hydrogen atom? So the focus of our study will be the hydrogen atom because we will learn about the hydrogen atom orbital. Now the question is, can we use DFT or density functional theory to predict all the properties of hydrogen atom? As we know from the lectures delivered by Dr. Fabian, quantum mechanics has successfully explained the hydrogen atom. However, quantum mechanics cannot be directly applied for multi-electron atoms without simplifications. there are simplifications need to be made before we can use quantum mechanics for the many-body electron problems. To ensure the validity, any simplification that we make must be tested on the hydrogen atom. So DFT is a quantum-based theory that simplifies the electron-electron interactions into a single electron system. So we use DFT for many electron system, but we are going to simplify the electron-electron interactions into a single electron system, like the one in hydrogen atom. The question is, can DFT explain the hydrogen atom? Can DFT explain the properties of hydrogen atom? Here in module A2, we will check the validity of DFT calculations with hydrogen atomic orbitals. So we are going to start with hydrogen atoms. Okay. The prerequisite for working on module A2 are completing module A1 that you guys have done it yesterday. You have collected your module. And the second one is read a book written by Dr. Febian titled Fisika Atomik dan Molekul, chapter 3. We, for the prerequisite one, we have done it before. So I hope you guys are able to answer the question from module A1. Anybody remember what are the physical and computational problems from module A1? You just collect the task yesterday. So I hope you still remember what are the physical problems and computational problems. Student from Unsud, anyone remember? What are the physical problems? Anyone? How about from ITERA? I don't see students. Naufal. I directly see Naufal when I open it. How about you, Naufal? Do you remember about the physical and computational problems?
Yeah, I remember, Dr. Lucia.
Can you mention some examples?
Okay. For the physical problems, like the initial density or initial density, or in the computational problem, like the device, different device, like
The CPU, right? Okay, thank you very much, Naufal. So the physical problems last time, after we perform our calculations, we need to match the valence electron configurations with the one from the Hans rule, from the textbook. And for the computational problem, one of the problem, as you mentioned, is about the CPU time. Which method can perform faster and which one will perform slower? And the second one, the question that we have answered before is, does the result of the FT calculations agree with the Hans rule? You guys have compared question number 4 in module A1. You guys have compared all your calculations. You check the valence electron configurations and then you compare it with the Hans rule. This state, we have to do this process to make sure that our calculation match with the Hans rule. This matching is for the validation of our calculation. So these two questions are the questions that we have answered in module A1. Now let's jump into the project description for module A2. Here we copy paste the question from module A2 to this slide. In module A2, we are asked to perform energy calculation for hydrogen, helium, carbon, oxygen, iron, and zinc atoms. with variation of Hartree-Fock and B3LYP, both with restricted method. So we have to add restricted method to our calculations. And the variation of basis sets are 321G, 631G, 321G star, and 631G DP. And we also have to add pop equals full and see if input options. Our task or your task is to perform comparison analysis and draw conclusions from 5 questions. So there are 5 questions provided in this module A2. So we have made a flow chart containing the workflow for module A2. So first, we start with our project description. This is our workflow, okay? So we start with the project description, and then next we model the case. After modeling the case, what we get is computational models and calculation design. The second stage, after we model our case and of course make our input file in the first step, next we perform the calculation. In performing the calculations, we will get results in numbers, but our results is still a raw data. We don't understand, and other people will not understand the results because it's still in raw data. So we have to do something with the data in order to be able to analyze it. The third step is tabulate the data. After tabulating, we will get our results. We will present our results in the form of tables and figures. As you have noticed, the question in module A2, there are questions that ask you to tabulate. There are also questions that ask you to visualize. In visualizing, we get the figures. The next stage is to analyze what we have tabulated. So what we analyze is what the tables and the figures that we have tabulated before. In analyzing, we will get a comprehensive explanation about our data. And the last step is to draw a conclusion. And our conclusion has to answer the goal that we have set, the objectives of module A2. That's our goal. So we start with the first step, model the case. The computational model from the project description before, from the question in module A2, we can identify what the computational model from the question. For the exchange correlations, there are 2, Hartree-Fock and B3LYP. So for the basis set, there are 4. And we also need, for the computational model, we also need to give the information about the atomic charge and spin multiplicity. And the last but not least is the position of the atom. So basically, there are 5 informations that we need to provide in order to build our computational model. First is exchange correlation. Second, basis set. Third, atomic charge. Fourth, spin multiplicity. And the fifth is the position of the atom. Okay. After we create our model, next is we perform our calculation. This is one of the example, but later I will demonstrate to you so we can calculate together some examples so we can see how to answer all the questions asked in module A2. Next, in performing the calculations, since we have a lot of calculations, we need to design our calculation. We need to plan in the beginning how many calculations that we are going to perform. We specify the total number of the calculations. And then, since we have a lot of calculations, we need to make a nomenclature for our input files. So for example, you run one file and then it's error, you have to rerun it again. You have to plan how will you name the file so that you don't give a funny name to your input files. For example, input file 1, input file 2, input file 3, and so on. But you need to give a nomenclature. So it's easy for you to understand, and it's also easy for others in case that you work in group. So one person calculate and the other person tabulate. So if you have agreed about the nomenclature in the beginning, it will be easy for each of you in the group to calculate and also to tabulate the results. Next is establish a calculation plan. Outline step-by-step plan for performing the calculations. For example, in module A2, there are 6 atoms. You have to calculate the energy for the 6 atoms. You need to plan which atoms should you calculate first and which should be last. And for the calculations, the same as module 1, we still do the single point energy calculation or SPA calculation. We use 6 variations of methods, 8 variations of methods, basis sets and exchange correlation. 4 basis sets and 2 exchange correlation. So in total, it's 8 variations of methods. And for the calculation techniques, remember that we have to add the restricted methods for closed shells and restricted open methods for the open shell. Later on, we will demonstrate how to do it to you also, so don't worry. Next, we tabulate. In the question in module 2, there are 3 questions that ask you to tabulate. Question number 1, 2, and 3. First, you have to tabulate the number of SCF cycles and job CPU time. Second, you have to tabulate the ground state energy. And the third, you have to tabulate the atomic orbitals and its energy. Those are the 3 questions that ask you to tabulate. And you also have to visualize the atomic orbitals with 2 different isosurface value. Okay. So next, I will move to Gauss view to demonstrate to you how we calculate with the simplest atom, which is hydrogen. I will move my screen to Gauss view. Okay, so here we are going to practice to calculate module 2 with hydrogen atom. I will demonstrate to you how we are going to do it with hydrogen atom. I build the atom. Okay, and then calculate. Job type is energy for the method. There are 8 methods, but I'm going to use P3LYP this time for the demonstration. So this is the FT and B3LYP. I use 631G for the basis set. The charge is 0 and the spin is doublet. It's restricted open. Okay. And then I move to the title. Single point energy calculation for hydrogen atom. I have to define it as full. No solvation, and then preview. Let's make sure that everything is okay. B3LYP 631G popful. Oh, it's this one. Okay. The charge is 0. The spin multiplicity is 2. It's hydrogen atom, and we also need to add JF in. Okay, let's submit our work.
Sorry, Dr. Lucia. Just can I have a question? Is it necessary to have the command for GF input, the keyword?
Actually, it is not necessary because we probably don't need it still this time.
Yeah, I think it's
Since it's in the question, should we skip it or do we just show it to the students? Actually, it's okay to skip it this time because for answering the questions, they don't really need it.
yeah, true. Maybe they can just yeah.
Okay.
Ignore that keyword.
Yes. Okay. Thank you, Dr. Mark. So I'm going to skip the JF input since you guys don't really need it this time. I will make new folder. For the name, I will choose hydrogen atom. The method is, I name it as 5. Oh, sorry, 6. And then the spin is doublet, so that's 2. Hopefully there is no error. Okay, what is the sign that our calculation is successful? We get a beautiful poem in the end. So if you have seen the poem, that means your calculation is successful. Okay, the calculation is done. Now we need to open our output file to answer the questions. Okay, this is the output file. Okay, first we have to tabulate the SJF cycles and also the job CPU time. I have prepared a spreadsheet, so I will open it for you. All right. In this spreadsheet, I name each sheet as question 0, question 1, up to 4. So actually we have question 1 up to 5, but I add question 0 here. Why? Because before we start to answer all the questions, we need to make sure what is the ground spin state of each atom. So that is the procedure that even though the questions, the project doesn't ask you, but you still have to do it to check and to make sure what is the ground spin state of each atom. We start with hydrogen atom. The spin for the hydrogen atom is only doublet, so there is no quartet spin state, so it is still safe for us. Here, IU has helped me to calculate all the calculations and tabulate it here. So we have all the results with us. This is the results for HAR3-FOC with each basis sets and B3LYP with each basis sets. This is the electronic energy in HAR3, but we have to convert it into electron volt. Why? because in electron volt, it's easier for us to compare with, for example, with the experimental data. So here we have our results in electron volt for hydrogen atoms. How do we get this? I will show you from the results before. Right click and go to the results, summary, and then this is the energy that you need to tabulate. This is still in Hartree, but then you have to convert it into electron volt. So after you calculate for both, for all the methods, you tabulate the results, and both in Hartree and electron volt. And after that, after you have all the results, then you make your analysis. Here I have written a simple analysis for the results of hydrogen atoms. If we compare the results from all methods, what we obtain, what we see here, for the doublet spin state, all the methods predict that the energy of hydrogen atom is negative. And it's negative 13.5.6. So it's no big difference among them. So it's almost the same for the results. So it's around negative 13.5 or 0.6. It means all the methods that we use here agree that the ground spin state of hydrogen is doublet. And as usual, we check with the Hans rule, because last time we have used Hans rule to, we check with the tables that contain the Hans rule. I will show you the table again. So what we obtain here is the ground state of hydrogen atom is doublet, and we go to the table with the Hans rule last time. Okay, let's check for hydrogen atom. This is the electron configuration, but the last information here, the number up here, it shows the spin state of the atom. So it's the hydrogen is in doublet state. So it's the same as our calculation. So we are safe for this. And here also we have provided the results for iron, but our calculations for iron, there are several errors that we faced here. But it's okay, we have the results, so we learn how to analyze these results here. So for example, here, we compare the results in cell I16 up to I19. I16 to I19, these are the results. As we take a look at these results, so, sorry, I explained too fast. So for the iron, we also calculate with all the basis sets. We tabulate the energy in singlet and triplet. We only consider singlet and triplet state here. And then it's still in Hartree. But after that, we will find the relative electronic energy in electron volt. Here I set the triplet as 0. So when I calculate the energy for the singlet, I minus it with the triplet state. Okay. So what we see here for our results in 4 cells that I marked here, it shows that according to, this is according to Hartree-Fock. The results is according to Hartree-Fock, but different basis sets. So as we can see here, according to some basis set, triplet is more stable because the singlet is positive. That means triplet is more stable than singlet. This is our calculation, okay? And then, but according to other basis sets, singlet is more stable because the result is negative. That's the first fact that we obtain from our results. Next, we compare the results in I21 up to I24. These are the results. The purple color means our calculation is error. So we don't have the results for that calculations. Okay, so as we compare the results here, what we see that there are calculations error when we use certain basis set. That's the fact that we obtain from these results. Thus, what we can conclude here with our results so far is that the ground spin state of iron maybe is not singlet nor triplet. So we probably is facing a physical problem here. So we check with the Hans rule, with the table. Let's check with the table for the iron. Now here is the iron. This is the electronic configuration, and this is the ground spin state. It's quintet. So we don't check the quintet state in our calculation. No wonder we get error here. No wonder we get conflict in our results because the ground spin state is actually quintet. So what should we do? We have to check with one spin multiplicity with another multiplicity, which is quintet. Okay. Let's move on to question 1. Question 1 asks us to tabulate the SCF cycle and job CPU time. Okay, remember guys, when we check the job CPU time, we have to do the calculation in the same CPU. Don't do the calculation with one method in one CPU and another method in different CPU. Later on, you cannot compare your results because it's not apple to apple. You are not using the same CPU. So make sure if you calculate one atom, make sure you use the same CPU for all the calculation, for all the methods, so that in the end, you can compare your results. So here, I will show you how to analyze the results that we have obtained so far. But before this, I will show you how to get the SCF, the data, the information for the SCF cycle and job CPU time. I will go back to the output file of my calculation before. Okay. Can you see it clearly? Or maybe I cannot enlarge this. So I will open it from Notepad so I can enlarge it so you guys can see it. I will close this. Okay, here it is. Yeah. Here we obtain the SCF done. This is the energy that we have tabulated before. the energy that we choose before in the beginning that I show you. And the information about the SCF cycle is here. We get 6 cycles for this file, for this calculation. Okay, so we will tabulate this number into our table before. And the other information that we need is job CPU time. Here it is. The job CPU time is 0 days, 0 hours, 0 minutes, and 6 seconds. So the job is performed in 6 seconds. So remember, guys, if you want to compare the job CPU time, you have to do the calculations in the same CPU for one atom, for each atom, right? Okay, let's see next. So we have, we input all the informations that we need into the table. Now we have the information about the SGF cycles for the doublet hydrogen in the doublet state. This is all the results. And the job CPU time in seconds. This is all the results. Now, what can we do with these results? What analysis that we can make? For the SGF cycles, we can compare the cell E3 up to E11. What we see with these results, the cycles are 4, 5, 4, 5, 5, 6, 5, 5. It means all methods have similar number of SGF cycles. They are similar. Not 4. If it's not 4, it's 5. Only one with 6 cycles. Okay. Next, for job CPU time, what can we do? What can we analyze from the job CPU time? Let's compare the data in cell H3 up to H11. These are all the data. As you see, the time needed to compute the calculation is 6 seconds, mostly 6 seconds. There are 5 seconds and there is 12 seconds when we use B3LYP 321G. I don't know why this one is different from others. It takes longer time than the others. So what conclusion that we can make from this data? In average, this is one of the way. You can use other ways too. This is one example that we want to give you. In average, all methods need 6.4 seconds. So I find the average for all the results. All methods need around 6.5 seconds to compute the job. However, one method, B3LYP 321G, needs the longest time among them. Those are the facts that we need to mention. For the iron, here I wrote, we cannot analyze these results since we have not found the ground spin state yet, because we haven't calculated the quintet state before. So after we calculate this quintet state, then we can analyze the results for this stage. Okay, next, we take a look. We were asked to tabulate the ground spin state energy. It means what you tabulate here is only the answer from the most stable state. So if you perform calculation in several spin state, for example, singlet, triplet, and also quintet, for the case of iron before, then you have to choose here in this question, you have to tabulate the energy only from the most stable one. So since hydrogen is only in a doublet state, then we have only one value here in electron volt. And then I also include, even though it is not asked in the question, but I also include the value from the experiment, because we have done this also in module A1. We were asked to compare the result with the experimental results. And these are the difference. So what can we conclude from these results? For the case of hydrogen atom, if we compare all the methods, we can see that the B3LYP is more accurate than Hartree-Fock. The result from B3LYP is closer to the experimental results. The difference is only 0.01. If we compare all the data in G3 to G6, which means this, the part that I choose here, from G3 to G6, we can see that the basis set 631G, this one, and also that one is more accurate. They predict more accurate results because the difference is the smallest as compared to 321G. We can see the basis set effect here. And the other information that we obtain here is that the D, P has no effect on our results. Why? Because when we use 631G only, the result that we get is negative 0.04. And even though we add the D, P, the result is still the same. It means the D and P gives no effects on our results because it stays the same. We also get the same conclusion when we compare the data in G8 up to G11. So you can see the basis set 631G predict more accurate result as compared to 321G. And the DP also has no effect to our results. And once again, we cannot analyze for the iron atom yet because in the previous slide, in the previous sheets, we haven't calculated for the quintet states. So that's the reason why we still cannot analyze these results. Okay, so we have obtained the ground spin state energy for the hydrogen atom. Next, let's move on into question 3. Question 3 asks us to tabulate the atomic orbital energy, if I'm not mistaken. Let me open the module again to make sure that we are doing the correct things. Tabulate the atomic orbitals and its energy. Okay, so we need to identify what the orbital is and how much the energy is. So we have to do two things here. We tabulate the atomic orbital and its energy. Okay. I will go back to my hydrogen before, my calculation before. It is hydrogen. Okay. We need to load the information from the GHCAL file. And we are going to visualize both orbitals with the ISO value of C.02. Right. Okay. I will change my background so you guys can see it clearly. Okay. Okay, so if we take a look at this orbital in all directions, we know that what orbital is it? Do you guys know? Anyone know? What orbital is this? This is orbital S. This is the number 1, orbital number 1. Okay, the one that I mark it here, orbital number 1 is orbital S. How we know that this is orbital S? It's from the shape. Yeah. So the first orbital for hydrogen atom is orbital S, and it contains how many electrons in here? It has one electron, as we can see from here. So if we want to write, so the name of this atomic orbital is 1s, orbital 1s. So that's what we are going to write in our tabulation for hydrogen atom. I will go back to my tabulation before. This is for hydrogen atom. This is 1s. And I tabulate the energy here. Remember, we have to do two things. First, we name the atomic orbital. And second, we tabulate the energy. The energy here is still in R3 that I tabulate, that we tabulate here. Okay, next is orbital number 2. Let's take a look. What is this orbital, guys? What do you think from the shape? It is also S, but it's an empty orbital. It is empty here. There's no electron. We have only one electron, which is in orbital 1s. Okay. So we only tabulate the energy for the 1s orbital. Right? That's for hydrogen atom. And then these are the examples that we have provided for iron. For the iron here, we don't need the 1s. We don't need the 1s. We only need to tabulate the atomic orbital energy for the valence electron for this part. Because in module 1, we have concentrated on valence electron only. So in module 2, we also continue with the valence electron. So the valence electron for the iron is 4s2 3d6. Once again, since we haven't calculated the ground spin state of for iron, this is only an example. This result is we cannot trust this result yet because it's not in the ground state. But we show this an example for you. So you only tabulate the atomic energy for the valence electron configuration. For the case of iron, it is 4s2 and 3d6. Okay, you guys can take a look for a while. I will, please excuse me to drink.
Yes, Dr. Lucia, maybe we can also take a break, like a 5 minutes break. Is that okay?
Oh, yeah, sure.
Okay. Thank you.
And Dr. Lucy. Okay.
Yes.
Please, Dr.
Thank you, Dr. Kara. I will share my screen again. All right, guys, before I continue to explain about question number 3, which is tabulating the atomic orbital energy, I should inform you that I made a mistake when giving you the information before. There is an information that we have to compare with this question. So for the tabulation, we have to do we have to tabulate the atomic orbital energy for all the orbital, for all the field orbital, not only the valence one, because there are informations that we need to understand with the core orbitals as well, with the core electrons as well. So that's please pay attention for that. For this question number 3, we need to tabulate the atomic orbital energy for all the field orbitals. Right. I want to show you something before I have demonstrated to you about the hydrogen atom. So we have seen that the first orbital in hydrogen atom, the energy is 0.07159. it is filled with 1 electron. And in the second orbital, which is an empty orbital, the energy is 0.12165. The energy of the second orbital is much higher than the energy of the first orbital. So I have written the value of both of this energy in the spreadsheet. I move to the spreadsheet now. Here, this is the value. Since I only calculate with this, the calculation that I demonstrate to you before, it is with this method. So the energy for 2s, I wrote it here. And the energy for 1s is there. 2s is empty, all right? And 1s is filled with only 1 electron. Now, let us calculate the helium atom also. So we move from hydrogen atom, we have only 1 electron. Move to helium atom, we have 2 electrons. So it is added with 1 electron only. So let's see what happened when we add another atom to the system. Another electron to the system. So I will make the input file for the helium this time. I will use the same method as before. It is the FT. The spin is restricted. The basis set is 631G. Right, it's singlet. Okay, it's RB3 alpha 631G, hopeful. Single point energy calculation for helium atom. The charge is 0. The multiplicity is 1. Our atom is helium, and these are the coordinates. Okay, we don't need additional keywords. Let's submit our job. Okay, this is helium with method 6. It's singlet. Let's wait for a while. Okay, it is done. We obtained the beautiful foam. Let's keep. Okay, I will open the output file for helium in singlet state. Why I calculate singlet? Because singlet is the stable, the ground spin state of for helium. Okay. In helium, we also have 2 orbitals. I visualize with the same ISO value, 0.02. The only difference between hydrogen and helium is the amount, the number of electrons. In hydrogen, we have 1 electron. In helium, we have 2 electrons. So as you can see, the first orbital, it has 2 electrons here. And what is the name of this first orbital? Is it SP or D orbital? It is S orbital. From the shape, we know that this is S orbital. So this is 1 S orbital, and it is filled with 2 electrons. This is the energy that we have to tabulate, and we have tabulated it in the spreadsheet. So I give different colors so we can compare later. that, and also this. This is the energy for 1s, and I'm going to tabulate the energy for 2s, which is 1.11978. This is positive, not negative. Okay, so what we have to see from here, what information that we can see from this comparison here, we compare the atomic orbital energy of hydrogen and the atomic orbital energy of helium. Hydrogen, it is in 1s, filled with 1 electron. The energy is minus 0.07159. In orbital 2s, it is empty, and the energy is 0.82165. Meanwhile, in the case of helium atom, the energy for 1s is negative 0.64981. This orbital has 2 electrons. So orbital in hydrogen has 1 electron, and in helium it has 2 electrons. And the empty orbital, which is 2s, the energy is 1.11978. What is the information that we get here? When we have only 1 electron in the s orbital, the energy is this. But as we add another electron to the same orbital, as we have another electron to the same orbital, the energy becomes negative 0.649. Which one is more stable according to you guys? Students from UNSUD? From these two values, what do you think is more stable? The top one or the bottom one? Which one is more stable? The more negative is more stable. So the 1s orbital in helium that has 2 electrons inside is more stable than the 1s orbital in hydrogen that has 1 electron inside. What does it mean? In one room, if there are more people, it will be more stable. If there is only 1 people, it is less stable. If there are 2 people, it becomes more stable. So that's the information that we need to tell you about these results. So if we have 2 electrons in the 1s orbital, the energy becomes way more stable than when it has only 1 electron. So for this question, please you don't only tabulate the energy for valence, the atomic energy for the valence orbital electrons, but also with the other orbitals as well, but only for the field orbital only. You don't need to tabulate the empty orbitals like what I did here. All right, is there any questions for this number, question number 3? Okay, then let's move on to question number 4, which is visualization. So we have obtained the helium before. I show you the helium. Oh, we have helium already before, right? And you guys have seen that for this shape, it means this is s orbital. It has 2 electrons inside. And remember, when you provide the information about electron configuration, make sure you validate it with the Hund's rule from the textbook. We need to visualize with 2 isosurface. This is the first visualization with 0.02 iso value, and I will change with the other one, 0.5 perhaps, or 0.3. Right. So this is the visualization for one s orbital in helium atom with the ASO value of 0.3. Okay, you guys just need to crop this figure and then put it in the module, the answer for module A2. Okay, so that's the end of the visualization. Now let's go back to the slides. So for the conclusion, what we have done so far, please wait for a while. Okay, so we have tabulate all the results in tables and figures. We also have performed a simple analysis before. This is for visualization, the example of visualization that we have provided. If you see the orbital with this shape, it means what orbital is this? This is orbital D, right? For orbital D, we have 5 combination. Okay, so if you see this picture in your visualization and match it with the information about the orbital, so you know which D orbital is this. The one shown in this visualization is DYZ. Okay, so you write it in your tabulation. This is DYZ orbital. We have made a comparison analysis during our tabulation before. We have identified the similarities and the differences between all our results. Okay, and the last, we draw the conclusion. For the conclusion, we need to answer the goal. The goal of this module is first to distinguish the physical and computational problems, and the second to check the validity of DFT calculations with hydrogen atomic orbitals. Now for the first objective or the first goal, we have learned the physical problem. You guys know that every time we see the electron configuration, we have to check it again with the Hans rule to make sure that our calculation or our module obtain the correct results. And for the computational problems, probably you will encounter the problems perhaps from the basis set. Maybe there are errors from the basis set, or maybe the job CPU time. Those are the computational problems. And what we have learned is to check the validity of DFT calculation with hydrogen atomic orbitals. In the beginning, we start with hydrogen atom. We have made sure that hydrogen atom is in the doublet state and the orbital matches the information in the Hans rule. Okay, guys, so this is the end of our quick review about module A2. Is there any question? I will start with the students from Unsud. Do you have questions? Guys, for module A2? No questions? Not yet? All right. Okay, no questions from Unsud. How about Itera? Dr. Vera?
Maybe let us give them like 2 minutes to think about the thing that they don't understand, because I hope they can ask many things today, because module A2 will due to this week. So this is your only chance to ask.
You will lose the chance after this, guys. After these 2 minutes, there is no more chance. All right, Dr. Vera. How about in UTM, Dr. Mark?
Yes. For now, there's no question, but let them maybe give them some time to think about it.
Right.
On their
Sure,
group.
sure. Maybe around 5 minutes. 2 minutes is too short. Only for breathing and then done. 5 minutes. Okay, let's wait for them.
There's a question from
Yeah, from
Right.
Dafa.
Java.
Can you hear my voice?
Yes, I
Yes.
can hear your voice.
Okay. So this module GF input will not use or not? Just my question. Thank you.
All right, thank you, Dava. For now, we don't need the GF input option.
Thank you,
Okay.
Dr. Sia.
You're welcome, Dava.
Yeah, is there any question? Is it clear? What will you tabulate and how do you tabulate?
They have no questions for now, but as they do the calculations and they start the tabulation, there will be a lot of questions from them.
If they are shy to ask, maybe they can write in the chat
Mhm.
so we can answer. In Bahasa, it's also okay.
Oh, Umbu is raising her hand. Go ahead, Umbu.
Good morning, Dr. Lucia. I wanna ask about the computational problem. Basis set, as you say, basis set and exchange correlation is a mathematical function, right? That right in computational. So it compute the energy specifically for the atomic for the atom. But if I want to calculate specifically for bonding, what combination of the basis set and exchange correlation the most the to get the result is more accurate for bonding. Thank you.
What kind of bonding do you mean, Umbu? Is it like covalent bond or non-covalent bond? Or
In physical science, there's a type of bond like p bond and like bond and anti bond like p bond and uh, p bond. If I want to calculate the specific value of that, how how can I do that?
Do you mean like sigma or
Yes, yes,
uh,
Dr. Vera. Like sigma bond, p bond.
oh, so this is the single, double, and triple bond. Actually, it will produce.
Oh, I see.
Yeah.
Oh,
So it's type of the covalent bond. So the single bond will be sigma bond. If I'm not
yes,
mistaken,
because
Dr. Mark know well. Because
I understand.
It is a covalent bond. So it's a covalent bond, he's asking.
yeah, he said about the P
Pi,
bond.
P sigma.
pi bond, sigma bond, yeah.
It's kind of covalent bond, right?
I think for now, currently we are only looking at a single element, right? A single
Yeah.
atom.
No
So
atom.
if you're looking at, I think bonds, pi bonds and sigma bonds, definitely the different basis set will have an effect on the accuracy of those bonding, right? Because he describes the orbitals, and we know that the covalent bonds, the overlapping of orbitals, so it would definitely the description of the orbital will affect the bond, the overlapping, right?
Thank you, Doctor.
Is it clear, Umbu? So you will
Uh,
use when you do it with molecules.
uh,
Yeah.
Thank you, Dr. Mark, Dr. Vera, Dr.
Before we continue, Rizka, do you have anything to add? Perhaps to the explanation that I have made or to the questions that the students have asked?
Just to add on the question earlier, so we know that overlapping of the orbitals also involve hybridization of the orbitals. So definitely polarization of the basis set of the orbitals are also important as one of the consideration when you are looking at the accuracy of the bonding. So polarization may also need to be included. Yeah. All right, Umbu. Yeah, just to add on to our discussion earlier.
Thank you, Dr. Mark.
Rizka,
From
san?
me, maybe not yet, Dr. Lucy.
Thank you, Rizka.
Is there any question? There's no one types the question in the chat also. So they are ready to complete the model A2 this week. Okay, no more question. Okay, if there is no question, so let us continue. So I would like to remind you guys that this week we will complete the module A2. And this week also we will give you the module A3. So you can read and also you can learn about the module A3. And we will have explanation like this today about the module A3. So we hope that you read before the explanation so you can ask more questions. So I will show you about the module A3. Share my screen. Sorry, there is Adhan here. So I will Sorry, let's we continue. So this is the module A3. So we will learn about the atomic ionization energy. So the objective of this module is design a plan for a simple calculation project. And then the second one is evaluate the accuracy of DFT calculation based on the atomic ionization energy. And from now on, you can search the CRC Handbook of Chemistry and Physics to find experimental values. So if you read the model A3, you will find the two reaction in here. The first reaction is how we add one electron in atom. So it become ionic atom. Here's the cations. And then the second one, the second reactions, when we take one electron in the atom. So from module A1 and module A2, you only learn about neutral atom. But in here, you will calculate the ions, the cations or the anions, to calculate the electron affinity and also ionization potential. So the prerequisite, of course, you need to complete the module A2. And then please access the CRC Handbook of Chemistry and Physics. For the project descriptions, your task is to calculate both ionization energies as described in reaction 1 and 2. So there is electron affinity and ionization potential. So please check these two quantities in the CRC Handbook of Chemistry and Physics. So they have all of the electron affinity or ionization potential for all atoms. And here, particularly in the ionization potential, so there is two, electron affinity and ionization potential. But in ionization potential, you have to calculate two cases, singly and doubly ionization. So you can calculate the first, we take one electron, and then we take another second electron. Your objects are hydrogen atom, one atom with a valence electron in the 2s orbital, one in 2p, one in 3s, and one in 3d and 4s. So there is total of 6 atoms, including hydrogen. So you can choose any atoms that has 2s orbital. The valence is 2s orbital, 2p, 3s, 3d, and 4s. And use B3LYP with variation of basis set, this basis set, and this basis set. So for the research and discussion, you can briefly explain what the electron affinity is and how to measure it according to CRC Handbook. So how people measure the electron affinity experimentally. So briefly explain as well how to read the table given by reference. And the second, please check in the CRC Handbook and then explain what the ionization potential is and how to measure it according to experiment. And briefly explain as well how to read the table given by reference 1. And then using the format of reaction 1 and 2, and then write the ionization reaction for the 6 atom. So hydrogen and then the 5 chosen atom. And then explain briefly the reason you choose the 5 atom other than hydrogens. So you cannot randomly pick because you have to put the reason here. And write your plan to finish this project. Consider when to use the restricted and unrestricted spin method in your analysis. Because in module A1 and A2, you already learned about when we have to use restricted and when we have to use unrestricted. And here, this is the first time that you write your plan to finish this project. So this is the kind of the calculation designs. So the first, what thing you do study literature from the CRC handbook because you learn about the electron affinity, ionization potentials, and also how to measure it. And then you do the calculation, for example, and then you compare with the experimental result. And then you can tabulate your results and their counterpart of the experimental results. Okay, maybe that's all about the short brief about the module A3. We will, for the next week, we will explain the module A3. Is there any question? We will give this module, I think today or tomorrow. Okay, maybe that's all.
Oh, I've actually given to my students at UTM.
Okay.
Yeah, so that they can have a look and at least discuss with their members.
Yes, the faster the better.
Yeah. I've also given them A4, the 4th module,
Okay.
so they can at least know what to expect in
Yeah.
upcoming modules.
And please make sure that you read the module A3 before our upcoming joint class.
Sorry, come again?
No, I tell the student that please make sure that they read the module A3 before our upcoming class
Okay.
because we will explain it like today. We explain about A2. For the next week, we will explain about the module A3.
Okay.
Is there any question or comment? Okay, before we close, is there any thing to add, Rizka?
No, Dr. Farah.
Okay, before we close our joint class, maybe there is a comment from Dr. Lucia or Dr. Mark about the module A2.
From me about module A2, there is no comment, but for module A3, maybe we need to remind the students, as you guys have seen what Dr. Farah has explained before, each module has different difficulties. And module A3, the level of difficulties is increasing as compared to the previous module. So we hope that you all discuss in group. So not only you are able to finish one question in each group, but you also know how to finish all the questions, how to answer all the questions in each group. So later on, you are able to catch up with module A3 as well, because the level of difficulties is increasing each time. I think that's it from me, Dr. Farah.
Okay, for Dr. Mark.
I agree with Dr. Lucia that students have to really discuss and plan well for their work because the level of difficulty is increasing. At the same time, I think there's no excuse for students not to discuss and plan their work well because not only group members do their own part, but they have to come together and come up with a discussion together, analyze the results and discuss together. So please do not wait to the last minute. So please do not wait to the last minute to do the assignment. Okay. So make sure that you agree with the deadlines that you have among your group members. I hope you guys can work well. Okay. With UTM students and also students from Indonesia. I hope you can communicate because I think there's no excuse because you have WhatsApp, right? You can always communicate. So please don't tell me that you assume that this is should be done on the last day. So please agree with your group members because I've received some complaints from groups. So I do not want to see that. All right, you're already fourth year. I believe you are able to work in groups. Okay, because it's a group assignment. I cannot let you do individually. Okay, you're already in the fourth year. You're going into the workforce. And if you can't work in a group, how are you going to work after you graduate? Yeah, you can make excuses now. You want to work individually. When you go to work, you have no excuse. If you can't work in groups, you can't work in the group environment. I don't think you can work. Yeah. So this is my advice. Please work it out. Okay, there's no excuse that you can't work together. All right, try to accommodate each other. I mean, sometimes everybody have their own difficulties, their own problems. So we try to give and take. All right. If you know that this person's character is like that, we try to come up with something. All right. Or maybe this person can do this, maybe he or she is better than at this. So let him or her do it. Okay, and then you can do something else. But at the same time, please discuss. Okay, the deadlines, discussion, results. It shouldn't be one person doing it, the discussion. Yeah. I hope you understand what I'm trying to say. Okay. Right. I think that's all from me. Thank you.
Yeah, thank you, Dr. Mark. So, okay, let's be close our joint class with the dua. Bismillahirrahmanirrahim. Subhanakallahumma wa bihamdika, asyhadu an la ilaha illa anta, astaghfiruka wa atubu ilaik. Alhamdulillah. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Picture?
Lah
Oh.
ya.
Let's take a picture. Let's take a picture. Kalau boleh login lah. Just take a picture sebab saya tak bawa.
Please open your, turn on your camera. Kalian semua enggak bisa? Nabila, can you take the picture?
Yes, Dr. Vera. Okay, please turn on your camera, and I'm sorry I cannot turn on the camera because my connection is unstable right now. Okay, now we have to slide. Ready? The first slide. 1, 2, 3. Wait. Let me check it. Now, the second slide. 1, 2, 3. It's done, Dr. Vera. Thank you.
Thank you, Dr. Nabila. Thank you, Dr. Mark and Dr. Lucia.
Thank you everyone. Thanks.